Hello, Algebra 1. Video lessons. We are going to talk through lesson 10 today, which is all about true and false equations. I like to remind you that there is an awesome pause button, looks kind of like this, that you can utilize, even a stop button, a rewind button, right? Fast forward button you probably won't need. Stop, rewind, pause, play, etc. All amazing things to do while I am trying to teach you some algebra skills. Okay, you should have your classwork in front of you and you should be taking notes. Exercise 1. Consider the statement, the President of the United States is a United States citizen. Is the statement a grammatically correct sentence? Yeah. What is the subject of the sentence? Subject, I'm going to say, is the president. What is the verb in the sentence? Is. Is the sentence true? Yes, it is, because the president is a United States citizen. Consider the statement, the President of France is a United States citizen. Is the statement a grammatically correct sentence? Yes. What is the subject of the sentence? Again, president. What is the verb? Again, I got this. It is. Is the sentence true? No. The President of France is not a United States citizen. You guys wondering what we're doing yet? Consider the statement 2 plus 3 equals 1 plus 4. This is a sentence. What is the verb of the sentence? The verb actually here is equals. Just like with the last two, we had the verb being is. Well, the verb here is equals. And what is the subject of the sentence? We have 2 plus 3 because it's the thing before the equals. Is this a true sentence? Consider the statement 2 plus 3 equals 9 plus 4. Is this statement a sentence? Yes. Is it true? No, it is not true. We have the verb and the subject, but that makes it false. Here, we're going to review. You remember math is a language. I often discuss math being a foreign language, that you really need to understand the building blocks before you can move on. Because math is a language. We talk about vocabulary, we talk about letters and numbers and words and what words mean in math. It's very much a language. We usually use English with this language, but it's a language. And when we see a statement, a math statement, like 2 plus 3 equals 1 plus 4, this is grammatically correct. The subject is 2 plus 3. The verb is equals or is equal to. This renames the subject. Okay, renames the subject. We say that this is true because the two numerical expressions evaluate to the same numerical value, 5, right? So, and then the last one, 2 plus 3 equals or is equal to 9 plus 4. This is also a grammatically correct sentence, but it's false because the subject, this would rename the subject, but it's not a true statement. It doesn't rename it correctly. So a few definitions. A number sentence is a statement of equality between two numerical expressions. A number sentence is said to be true if both numerical expressions are equivalent. That is, both evaluate the same number. It's said to be false otherwise. True and false are called truth values. Okay, the words true and false are called truth values. All right, we have a ton of exercises here, and we are going to name them true or false. I'm going to go through, let's see, the first maybe 6, and then I'm going to make you try the last 6 on your own. You may have fun with a calculator at this point to see if things are true or false, but I'm going to go through the first 6 live, and then I'm going to go through the next, pushing pause, really. Let's see. Well, that'd be a not, right? Okay, not true. 1/2 plus 5/8. If I get at my, well, let's see. 2 goes into 8 4 times. 4 times 1 is 4. Oops. Add across 9/8. 9/8 is the same as 1.125. If I check out this, 1.2 minus 0.075 is also 1.125, so that's true. PEMDAS, 71 times 603, because that's parentheses, times 5876. Big number. Actually, I don't even have to do this. If I look, this got it's all the same numbers. They just got regrouped and put in different orders, which is the commutative and the associative properties, which hold true for multiplication. So no matter what order I multiply those in, I'm going to get the same answer. So I don't need to actually do the math. True. Let's see. 13 times 175. 13 times 90. 85 times 13. Well, if I factor out a 13, I get 90 plus 85, which is 175. So these are equal. Therefore, it's true. Oh goodness, please, students, I'm begging you. You cannot distribute exponents when they are separated by a plus or minus. This is a binomial separated by a plus. I cannot distribute that power to get 7 squared plus 9 squared. Okay, this really is 7 plus 9, 7 plus 9. Okay, you can FOIL that like we would if it were variables, or you can add 7 plus 9 and square it, but it is not equal. Okay, last one I'm doing with you, pi 3.141. Pi is an irrational number that goes on forever, so I cannot truncate the decimals at all and get a correct answer. Oh, sorry. False. Okay, so I'm on F. We're going to do the next few. I'm going to write true or false, but I'm going to push pause. Okay, need you guys to try these on your own. I'm pushing pause. You should too. All right, check those out. Be sure to bring them up to me tomorrow if you're not sure why these are all false except J, which is true. Okay, last page. I'm pushing pause. Push pause and try them on your own. All right, there we go. The last 4. Make sure you let me know if you have any questions. All right, exercise 3. Could a number sentence be both true and false? Could a number sentence be neither true nor false? A number sentence has a numerical expression that always equals a number. So a number sentence, if we have an equal, we're always going to get a number and a number, okay, on the left and the right. Either these match, or they don't match, okay? So I have to say that a numerical sentence is either true or false. Never both. An algebraic equation is a statement of equality between two expressions. And algebraic equations can be number sentences when both expressions are numerical, but often they contain symbols whose values have not yet been determined. Okay, welcome to algebra. They contain symbols like x. Where is x? So, which of the following are algebraic equations? I've got numbers and letters. I have numbers and symbols. I have lots of symbols. I have numbers and symbols. All of them are algebraic equations. Okay? Which of them are also number sentences? Let's see. Number sentences. I'm going to highlight in red. A number sentence, I've got this one, okay, because I have a symbol there. Here I have a symbol and a number, so that would be 4. Lots of numbers that are equal. 5, lots of numbers and symbols that are equal. Yeah, I think that's good. Okay, those are number sentences. For each number sentence, state whether the number sentence is true or false. Let's circle those in blue. True or false. The first one wasn't a number sentence. So 2, I have 10 pi to the 4th plus 3 equals 99 pi squared. Yep, I'm going to say that one there is false. The next one, pi plus pi equals 2 pi. That is true. What is next? Number 4. Let's look at number 4. 1/2 plus 1/2 equals 2/4. That is false. Okay, the number does not work out. 1/2 plus 1/2 equals 2/2, which is 1, a whole number. Okay, so that is false. The last one. 79 pi cubed plus 70 pi squared minus 56 pi plus 87 is equal to that mess. Okay, that is just plain old false. If I took the left side of this equation and I divided it by pi squared, I would actually get 79 pi plus 70 minus 56 over pi, plus 87 over pi squared. Okay, it's just not equal. So I would say that one is, in fact, false. That was kind of painful, wasn't it? When algebraic equations contain a symbol whose value has not yet been determined, we use analysis to determine whether the equation is true for all the possible values of the variable, whether the equation is true for a certain set of possible values of the variables, or the equation is never true for any of the possible values of the variable. For each of the 3 cases, write an algebraic expression that would be correctly described by that case. Use only the variable x, where x represents a real number. So part A, if we wanted to come up with an equation, this would be so much fun in class, where the equation is true for all the possible values of the variable. We could come up with something that used the distributive property. We could say 2 times x plus 3 is in fact equal to 2x plus 6. No matter what I plug in for x, the left side of my equal sign is going to equal the right side of my equal sign. Okay? Because the left and the right side are equivalent, so it doesn't matter. Okay. B, the equation is true for a certain set of possible variables. So now I just need an algebraic expression. X plus 5 is equal to 11, which is true for x equals 6, and only x equals 6. Everything else would be false. All right, how about C? I need never true. Well, I really like this answer. X squared equals -1. I can't plug anything in for x and square it to give myself a negative answer, because negative times negative is positive every day of the week. Okay? All right, consider the following scenario. Julie is 300 feet away from her friend's front porch and observes someone is sitting on the porch. Given that she did not specify otherwise, we would assume that the someone Julie thinks she sees is a human. We cannot guarantee that Julie's observational statement is true. It could be that Julie's friend has something on the porch that merely looks like a human from far away. Julie assumes she's correct and moves closer to see if she can figure out who it is. As she nears the porch, she declares, "Ah, it is our friend, John Barry." Not just John Barry. So in math, we do a lot of observation. We observe a situation, we make statements, we believe these statements to be true. Just like Julie used the word someone to make us believe that it was a human. In math, we use variables in our statements to represent quantities not yet known. So we use X because we don't know what it is. We want to represent it. Just as Julie, we're going to get closer to study these equations to find out if someone exists and who it might be. So we assumed that the someone Julie referred to as a human, and then we would look closer and closer, and yep, it was a human, but not the human that we thought. So a variable can represent an integer, or even an integer. Like Julie represented a human. Our variables usually represent integers. Whole numbers. So really verifying our variable is important. It's what we're talking about. Which in this case, we call it our domain. Okay, domain, it's a really, really important vocabulary word. And it's really the type of number the variable represents. Okay, it's our domain. So let's talk about that. Name a value of the variable that would make each equation a true number sentence. Here are several examples of how we can name the value of the variable. So our equation is w squared equals 4. We can represent any real number we care to choose. Any real number. It's domain. Okay, we're looking for w's. We want any real number, its domain. If we choose to let w equal 5, then the number sentence is false because 5 squared is not equal to 4. If we let w equal 2, then the statement is true. Is there another value for w that would also make the sentence true? Okay, let w equal -2. Then w squared equals 4 is true. So this is true when w equals -2. It's also true if w equals -2. It's true for both of them. Okay, our domain of w equals -2 and w equals true make for a true statement. Okay, let's try a few more. There might be more than one option for what numerical values to write, and feel free to write more than one possibility. Warning, some of these are tricky. Keep your wits about you. Thank you, textbook. We will try. Let blank. Then 7 plus x equals 12 is true. So what do we want x to equal? We're going to say 5. B, let blank. Then 3r plus 0.5 equals 37 over 2 is true. So 37 divided by 2 is 18.5. So 3r plus 0.5, what is r? Well, if I take away the 0.5, I got 18. What times r is 18? If we let r equal 6, 3 times 6 is 18, plus 0.5 equals 37 over 2, which is 18.5. Okay, let m cubed equals negative 25 is true for, I need something times something times something equals negative 125. I know 25 times 25 times 25 is 125, but negative. Well, luckily, if we have negative times negative, we get positive. Times negative again, we get negative. So I got it, but we want not 25, it's 5. My bad. Sorry. M equals negative 5. Cool. A number x and its square, x squared, have the same value when, well, that only works once, when x equals 1, x squared equals 1, or x equals 0. 0 squared is still 0. The average of 7 and n is negative 8 if, average. So 7 plus n over 2 equals negative 8. So I need a really small number. 8 times 2 is 16. So if I want to go negative to get to negative 16, I think 23. So if I went 7 and a negative 23, 7 plus negative 23 is negative 16, is negative 8. Whew, that was a tough one. I had to go back to my number line, right? I had to go this way to get to negative 23 before I could find it. All right, last slide. Let blank, then 2 equals a plus a is true. I think that works for anything because 2a equals a plus a is actually true. So no matter what I put in for a, I'm going to get a true statement. So I can say a equals any real number. All right, q plus 67 equals q plus 68. Nothing. That's not true. Okay, it doesn't work. So it's a false statement. Awesome, good job. You're all done. Okay, good work.